Start our class. Okay, then fine. Okay, if we apply the ramp signal, okay, if we apply the ramp has an input signal, then how the output will be? Okay, how the output will be? We will see it. Okay, that means below the cutoff region. Okay, this is your cutoff region. Okay, this is your cutoff region, and this is your this is your cutoff region, and this is your active region, and this is your saturation region. Okay, this is your saturation region. Okay, therefore, as we know that in cutoff region, transistor is an open switch. Therefore, the whatever the input that will be draws from the output. Okay, therefore output and the input are same in the cutoff region. Okay, in the active region, it is a amplified version. Okay, therefore there will be some small deviation. Okay, or this is the voltage here. You can observe you can observe the current. Okay, you can observe the current. Okay, in cutoff region, it is an open switch. Therefore, you are going to have a zero current. Okay, as the current is zero means voltage will be maximum. Here the same process. Okay, output is nothing but a VCC minus I into R. As the I is zero, you may get maximum voltage as VCC. Therefore, our output voltage, this is our voltage waveform. Okay, voltage will be as similar to your input. Okay, current is zero. Current is zero. In active region, the current will be increases linearly. Okay, the current will be increases. Okay, in saturation, the current will be maintained constant. Okay, the current will be maintained constant. Here also, voltage has similar to a OCC curve. In mission slab, you may draw the OCC curve. Okay, as a curve, it may be maintained constant. Like this, it is going to maintain the constant because the drop is going to maintain constant. Okay, therefore, this is your output voltage. This is our output voltage. In saturation part, it will be maintained constant. In active part, it is an amplified version, or it may deviate from your input. In cutoff, your output voltage will be as similar to the input because the current will be zero. Okay, we can observe it in current waveform. Current will be zero in cutoff region, and in active region it is linear increases. In saturation, it will be maintained constant. Okay, if we apply the ramp signal, you may get this type of waveform at the output terminal. Okay, if we apply the sinusoidal signal, this type of work. Okay, generally we concentrate on the current signals only because it is a transistor. Okay, this type of signal you are going to get at the output terminal, and it may be ramp. You may get this type of terminal at the output terminal. Okay, I think so. You are clear with this transistor has a clipper. Okay, transistor has a clipper. Okay, basically depending upon its regions. Okay, once again depending on its regions, it is going to clipping the output waveform. Okay, output waveform, and we see the different types of different inputs, different outputs we had observed. Okay, now what I had explained in previous graph, I have mentioned as a theory in this slide. Okay, once you can go through this slide. Okay, next one is the emitter couple. Okay, in previous slide I had explained the circuit. Okay, how is the circuit is working, I had explained in this slide. Okay, for your material purpose. Okay, you can go through this. I will explain by seeing the circuit diagram. Okay, next one is the emitter coupled transistor. Okay, last topic in your clippers. Emitter coupled transistor, or you can call it as a two-level clipper. Okay, you can call it as a two-level. If you see the previous one, it has clipper only at one portion. Okay, we have in positive cycle, it has clipper only at one. If you go in negative cycle, it may clip only one. Okay, if you consider only positive cycle, it is clipping at one portion only. Okay, but when coming to the emitter couple, it will clip in positive cycle, it is going to clipping at two parts. Okay, two levels we are going to clip. Okay, that's why we are going to call it as a two-level clipper. It is also called as a two-level clipper. Okay, otherwise it emitter couple, very important concept. Okay, emitter couple clipper, they are going to call it as an emitter couple because previous one it is a self bias one. It is an emitter follower bias. Here we are going to apply the emitter follower. Okay, for biasing these transistors. Okay, okay then, and this is the circuit diagram. This is the circuit diagram for emitter coupled transistor. Okay, here if we observe the circuit diagram, you find the two transistors Q1 and Q2. Okay, Q1 and Q2 you are going to find the two transistors, and we are going to collecting the output across Q2. We are collecting the output across Q2, and we are applying the input across Q1. Okay, here we are going to applying the input signal. Okay, And one more thing here you have to keep in mind, for the input signal we are not biasing. Okay, that means here, okay, as previously we have said, for the base we are going to connecting the DC supply, and for the DC supply we are connecting in series with an input signal. Okay, like this we have discussed in previous. Okay, so here this, for this transistor there is no DC. Okay, that means directly input is driving your transistor. When the input voltage is sufficient, then this transistor will move to from cutoff to active, and if it is sufficient, it may move from active to saturation. That means depending on the input signal. Okay, it will be operated. But when coming to the Q2 transistor, it is a self biased. Okay, we had applied a constant DC voltage. We had applied a constant DC voltage has to a base, has the input to the base of Q2. Therefore, your base current IB2, okay, it will maintain constant. Therefore, and we will maintain this transistor in active region. Okay, we will keep this transistor in active region by using this transistor, by using the VBB voltage. Okay, by using the VBB voltage, we are going to keep this transistor in active region. Okay, Q2 will be in active region, and Q1 initially we are going to considering the sinusoidal signal. We are going to considering the sinusoidal signal. Okay, since sinusoidal signal, generally for this concept, first they may consider the negative cycle. Okay, for simplicity, they may consider this type of waveform. Yeah, we can consider any type. Yeah, whatever maybe, first we consider the negative cycle or positive cycle, or first if we consider the positive or negative, we will get the same waveform. Okay, the shape won't be much matter. But if you go in our textbook, if you watch our textbook, they may give this type of waveform. First they may take, up to now we have considered this type of waveforms. Okay, first we have studied the positive cycle, and next we have studied the negative cycle. Okay, whatever maybe you will get the same shape. Okay, therefore we will see the both. Okay, we will see the both. If it is at zero potential, okay, if we take the positive cycle, yeah, if it is at zero potential, okay, that means we had applied 0 volts and base current will be 0. Therefore, the transistor will be in cutoff region. Therefore, initially, or if we apply a negative cycle also, if we apply a negative cycle also, this transistor will be in cutoff only. Okay, complete negative cycle, it will be in cutoff region. Okay, therefore, before starting this experiment or before starting this circuit, this Q1 should be in cutoff region and Q2 should be in active region. We have to set like that. Okay, we have to see that Q1 should be in cutoff region and Q2 should be in active region by adjusting this PBB. Okay, when Q1 is in cutoff region means Q1 is open switch. When Q1 is open switch, this IC current will be 0. This IC, because it is open switch, therefore IC1 will be 0. Therefore entire current from VCC, entire current flows through the IC2. Okay, IC2, and since it is a active region means it is in amplified version. Therefore, this switch is we can treat as a closed switch. Okay, therefore this current will flows to the IC2, current will be flows through the IE2 and to the IE, and then it will be grounded. Therefore, IC2 current will be can be actually, if you want to agree practically, we may take as IB plus IE. Okay, this is your IC current. Okay, or you can, sorry, IE equal to, not IC equal to, IE equal to. Okay, IE current equal to, okay, IE, that means this current. Okay, IE current is nothing but what of the current entering at this point. Okay, to this point IB current is entering. Similarly, IC current is also entering. Therefore, IE equal to, we can write that IB plus IC, where IB will be in microamperes. Okay, IB will be microamperes, IC will be milliamperes. Therefore, for simplicity, we can neglect the IB. Okay, because it is a small current, we can neglect the IB. Okay, for simplicity. That's why we are considering that in this experiment, we are going to considering that IE equal to IC2, IE equal to IC2. Okay, therefore starting. Okay, these are at the time of starting. At the time of starting, IC will be 0. And this transistor will be in cutoff region, and this transistor will be active region, and there will be an IE2 current flowing through this resistance. Therefore, IE2 current will be equal to the IC2. IE2 current will be equal to the IC2, and IE equal to IE2. IE equal to IE2, and IE1 equal to 0 at the time of starting. Okay, this is at the time of starting, these values will be. Okay, and therefore your output voltage. Okay, your output voltage will be A is nothing but a, as we seen previous, output voltage equal to VCC minus drop across this resistance. Okay, this is our output voltage. Therefore, our output voltage is nothing but a VCC minus IC2 IC to RC. So IC to RC. This is our output voltage. Since we have applied the base current as constant, okay, our base voltage, okay, base voltage is a DC voltage, okay, which is a constant, okay. Therefore, due to this base voltage, this current will be constant. IB current will be constant, okay. As the IB is constant, IC will be maintained constant, okay. Therefore, as this current is maintained constant, this drop will be maintained constant. As it is constant, output voltage will be maintained constant. Unless this transistor is in cutoff zone, okay, Q1 is in cutoff zone, okay, our output voltage will be maintained constant. And that voltage is nothing but a VCC minus IC2 into RC. Okay, this is the output voltage. Okay, I think so you have understand. If you have any doubt, you can unmute your mic and you can ask. Okay, our output voltage, what I have said, until your transistor Q1 is in cutoff zone, Q1 is in cutoff zone, and the output voltage is going to maintain constant at this level. Okay, when the Q1 will be in cutoff zone, when this voltage, base emitter voltage, okay, because the transistor is nothing but a back-to-back connected diodes, okay, back-to-back, and that means here we have one diode, and here also we may have the another diode, okay, back-to-back connected diodes, okay. Therefore, when the base emitter junction is forward bias by applying this voltage, that means suppose if I take it as a silicon diode, when you apply the 0.7 volts here, when you apply the 0.7 volts here, this diode will be forward bias, and this transistor moves from cutoff to the active region, okay, and then it moves to the active region, or it may move to the saturation, okay. If you switch on this transistor, if you want to switch on this transistor, this base emitter voltage, okay, that means whatever we are applying input, our input is nothing but we are applying between the base and the emitter, okay. This is both will be connected to the ground, okay, base and the emitter, okay. This is our ground potential, okay. This voltage, base emitter voltage, should be greater than 0.7, okay. That means our input voltage. If it is a silicon, okay, silicon, if we made this transistor by silicon, okay, otherwise you can say voltage should be greater than cut down voltage. Simply when the input voltage is greater than cut down voltage, this transistor comes to on, okay. That means before this point, this transistor will be off, okay. That means if you take it as a positive cycle, now you will find the difference, okay. Why in testing they have taken first negative cycle, okay. If you take the positive cycle up to the cut down voltage, that means up to 0.7, and the transistor will be off, okay. From 0.7 the transistor will be on. Therefore, you may find this portion, okay, in positive cycle. If you see the output characteristics, this is your transfer characteristics drawn between output voltage versus input voltage, okay. Now we are in positive cycle. Positive cycle means we have to transfer characteristics will be in first coordinate, okay. In first coordinate we are getting a constant voltage, okay, where up to which instant, up to the cut down voltage, okay. This V1 or VI1, this VI1 is nothing but your cut down voltage, okay. It may be up to 0.7, okay, if it is a silicon, okay. Up to this point we are maintaining a constant voltage. This voltage will be constant if you take the positive cycle. If you take the negative cycle, if you consider the negative cycle, the complete negative cycle, this transistor will be in cutoff, because we are applying a negative voltage here. This diode will be in reverse bias, okay. Therefore, in complete negative cycle, the transistor will be in cutoff to the zone, and we are going to maintain the output voltage at VCC minus IC into RC. This voltage will be. Therefore, for complete negative cycle, this is your negative cycle, okay. In negative cycle, complete negative cycle, you are going to maintain a constant voltage, that is VCC minus IC into RC. This is your negative. Because why we are maintaining this voltage constant means this transistor is off. Once this transistor is off, and for this Q2 we are applying a constant voltage, therefore base current will be maintained constant. When you are maintaining this current constant, this current will be maintained constant, okay. Therefore this transistor is cut off, okay, up to which instant, yeah, up to the cut down voltage of your transistor, okay, up to the cut down voltage. That means this is your negative cycle, and positive cycle up to the cut down voltage, okay, up to this time, okay. Therefore, for explanation it will be easy. If you take the first negative cycle, and then if we take the positive cycle, negative cycle, we may say that our transistor is in cutoff zone. Therefore, this will maintain constant voltage. In positive cycle also, up to the cut down voltage V gamma. Okay, the up to the V gamma, we are going to our transistor will be in cutoff zone only, and we are maintaining a constant voltage. Okay, that voltage is nothing but VCC minus IC Gaussian. For this purpose, for explanation point, they have taken. Otherwise, if we take the first positive, first we will draw only in positive cycle, and then we will draw the negative cycle. Okay, both if you combine both, you may get the same shape. Okay, the whole you has your wish. You can go for any type of waveform. Okay, but initially this transistor should be in cutoff zone. Okay, therefore this transistor is in cutoff zone. Now we had applied the input, and the input voltage is greater than the cut down voltage. Okay, input voltage is up to now, I think so you have understand. Okay, when the Q1 is in cutoff zone, we are getting a constant voltage. We are getting a constant voltage. Now the input voltage is rising. Okay, input voltage rises greater than cut down voltage. When it is greater than cut down voltage, this junction gets forward bias. Okay, when this junction is forward bias, okay, the switch is, this transistor is going to be on. Okay, that means the transistor moves from cutoff to active region. Cutoff to active region. When it is moving to active region, this current, okay, since this transistor is on, IC1 current will be flow. Okay, IC1 current will flowing in the circuit, and therefore due to this IC1, IE1 current will be flow, because IC is equal to IE. If you neglect this base current, if you neglect this base, because base current is very minimum, if you neglect it, IC equal to IE. Okay, therefore this current IE current will be flowing. Okay, and this current IE current is a variable current, because IC is varying. Why IC is varying? Because IB is varying. Why IB is varying? Here the input voltage is not a constant voltage. Our input voltage is a sinusoidal voltage. Our input voltage is a sinusoidal. Therefore, with respect to time, voltage is increasing. With respect to time, voltage is increasing. As the voltage is increasing, current will be increased. Okay, as this current is increasing, this current IC current also increases. As IC increases, IE also increasing. Okay, therefore, the as this IE is increasing, okay, as this IE is increasing, it will change this IE2, because this IE will be maintained constant. Okay, this IE will be maintained because this resistance is going to be constant, and this IE is constant. This IE1 is increasing, this IE2 is going to be vary. Okay, therefore as this is has IC2 equal to IE2. Okay, therefore as it is decreasing, this drop will be decreasing. IC into RC drop will be decreasing. As therefore output will be increasing. Output will be increasing. Okay, when it is in the active region, when Q1 is in the active region, as the Q1 is in the active region, the base current is keep on increasing, means IC, as we seen previously, as the base current is increasing, IC current will be increasing. As the IC increasing, IE will be increasing. Okay, therefore due to this, IE2 decreases. As IE2 decreases, IC2 gets decreased. Okay, therefore as IC2 decreases, this drop will be decreased. Okay, as this dropping decreases means output voltage is nothing but a VCC minus drop. Okay, therefore this drop is decreasing, or output voltage will be increases. Output voltage will be increases. Okay, then fine. If the voltage, if the Q1 base voltage keep on increasing, this transistor Q1 may move to the saturation. Okay, Q1 may move to the from active region to saturation. When it is in saturation, okay, here you can observe. Okay, in saturation, you can go for by writing the output equation, we can find out, or simply by common sense. Okay, by seeing the common sense, when it is in saturation means this transistor is a closed switch. This transistor is closed switch means here we are not offering any resistance. Okay, in active region we may have some resistance. Okay, since it is in saturation, in this path, okay, from VCC, what you are going to getting the current, we'll see the two paths, IC1 and IC2. Okay, if you go for IC1, in this path it is in saturation mode, therefore it is offering the low resistance, therefore maximum current, total current will flow in this direction only. This current will be goes to the 0. This current will be when this transistor Q1 comes to the saturation mode. When Q1 comes to the saturation, the current in this path will be increases, because in this path having the fluorescence. It is in saturation mode. Therefore, this current may goes to zero. What indicates when this current goes to zero? When this transistor is in cutoff zone. When it is open circuited, then the current will be zero. That means when this transistor move to saturation, it makes the Q2 as a cutoff. It makes the Q2 in cutoff zone. Okay. Okay, that means from the starting, if you observe, when the transistor is in cutoff zone, this Q2 is in active region. Okay, when Q1 is in active region, Q2 will be also in active region, but it moves. Okay, that means if you draw the transfer characteristics, previously it may be Q2 may be operating at here. Okay, Q2 may be operating here. Q1 may be operating in cutoff zone. Q1, this is a Q1 output characteristics. Okay, this is Q2. Okay, Q1 is in cutoff zone. Okay, Q2 is in active zone. When this point moves to the active, when this point Q1 operating point moves from cutoff to active region, Q2 moves from active to near to the cutoff zone. Okay, it moves downwards. Okay, it moves downwards and it will be near to the cutoff zone. When the Q1 moves to the saturation, Q1 moves to saturation, this point moves to the cutoff zone. Okay, therefore Q2 will be operating at cutoff. Okay, Q2 will be operating at cutoff and Q1 will be operating in saturation. When Q2 is cutoff means this, then only this kind will be goes to zero. That means this kind is zero means this drop will be zero. Okay, this drop will be zero. Therefore, our output voltage is nothing but a VCC. Therefore, we are going to maintain output voltage again constant at VCC. We are going to maintain the output voltage again at VCC. Okay. Therefore, this drop will be goes to zero. When this drop will be zero, when the transistor is in cutoff saturation region. Otherwise, if you draw the output equation here, also, you will get the same. Okay, that is nothing but a VBB. I am writing the KVL at the output loop. Okay, VBB plus here we may have the VCE voltage. Okay, VCE voltage we may have. Okay, and then here we may have the drop. The drop is nothing but a RE into IE1. Okay, the current through this branch is nothing but IE1 plus IE2. IE2. Okay, minus okay, minus this is minus VEE voltage. Okay, minus VEE. Okay, now in order to make this transistor off, okay, in order to make Q2 in off stage, this voltage, okay, that is VCE voltage should be less than cut down voltage. Okay, then only this junction will be reverse bias and this transistor will be off. That means this voltage, okay, VCE voltage should be less than cut down voltage. That means if you keep VCE in one side, okay, VCE equal to, if you take remaining to one side, you may get the VEE minus VBB minus this drop IE into IE, RE into IE1 plus IE2. Okay, this VBB is constant. Okay, this VBB is constant. This is our voltage. Okay, VBB is a constant voltage, and then here IE is increasing. Has IE because it moves to saturation. It is moving from cutoff. When it is cut off, the IE1 value is 0. When it comes to active region, and this maybe goes to the 1 ampere or 2 amperes. When it goes to saturation, okay, it keep on increasing and reaches to saturation. That is final value. Okay, that means IE1 is increasing. As IE1 is increasing means minus value. Okay, minus value is increasing. Okay, when minus value is increasing means this voltage will be decreases automatically. VCE voltage. Okay, that means as we are increasing the IE1, what it will do means it will reduce the VCE voltage. That means this junction voltage is going to be reduced. Okay, when it will be less than the cut down voltage, the diode present at this junction, because the transistor is a two diodes. Here we have one diode and here we may have another diode. This diode will be in reverse bias and this transistor going to the cutoff region. This is from the derivation, or simply by equation we can say that when this current increases, this diode will move to the cutoff. Otherwise, by common sense also we can say, okay, the current at here, okay, IC current will be see the two paths. Okay, this path is having the resistance, therefore maximum current will flow in this direction. Therefore, definitely this current is going to 0. If this current is 0 means that indicates this transistor is off. When this transistor Q2 is off, then only you will get the 0 current here. Okay. Therefore, when this is in saturation mode, Q2 will be off. Once Q2 is off means you may get the output voltage as VCC only, because VCC minus this drop is 0. Okay, this current is 0, therefore this drop will be 0. Therefore, we get a constant voltage here. Okay, this is the transfer characteristics. If we want to plot the output characteristics, okay, up to the, suppose I want to drawing the input waveform. This is my input waveform. Up to the cut down voltage, we are going to get a constant voltage, and then suppose this is your VCC point. Okay, up to the VCC, output voltage will be increases linearly. From VCC again it will maintain constant, and again it decreases, and again it is going to maintain constant. Okay, that means our output you may get like this. Okay, this point is nothing but your VCC. Okay, here we should not get the doubt that if the VCC is greater than input voltage, that means if suppose VCC is 3 volts, okay, input voltage is some 10 volts. Okay, that means input is 10 volts. Okay, this is your input voltage. Your peak value is 10. Okay, your VCC is 3 volts. Therefore, at 3 volts, above the 3 volts is going to be clipped. Above the 3 volts, you are going to get clipping. Suppose reverse if we assume, okay, this is the 10 volts and this is your 3 volts. Okay, that means you won't get any clipping portion. Okay, VCC will be at 10 volts. VCC is your 10 volts, but input voltage is only 3 volts. It means starts from cut down and it reaches to 3 volts and again decreases, and this may be your cut down voltage. Your input voltage won't be any cut. Okay, it won't be any clipping in our input voltage. Okay, definitely your VCC should be less than your input voltage. Then only you will get a clipping portion. Okay, this clipping portion. Okay, therefore you should not get this doubt. Okay, if the VCC is 10 volts, what happens? Okay, if the VCC will not be at 10 volts, okay, it should be less than the that voltage. Okay, it should be less than. Okay, that's fine. Okay. Okay, then fine. Okay, therefore your output voltage will be like this shape. Okay, it will be start from cut down voltage. Okay, if it is a positive cycle. Okay, and increases up to the VCC, and then it decreases, and in negative cycle, the voltage will be maintained constant. In negative cycle, this voltage is nothing but a VCC minus ICRC. Okay, VCC minus ICRC, and this voltage is what Okay, I think so. You have to understand this transistor clipper. Once again, I will draw it here neatly. Okay, like this you may get the output terminal. Okay, this is our output voltage. Okay, this is regarding our transistor clipper. Okay, then fine. If we have any doubts, okay, if we have any doubts, please ask. Okay, Sunil sir is waiting for second class. Okay, time is over. If we have any doubts regarding the transistor clipper, quickly within 1 or 2 minutes.